You're listening to the STEMxm podcast, highlighting women in the fields of science, technology, engineering, and mathematics. And now, your host, Mel the Engineer.
Hello, and thank you for joining us here for episode 25 of the STEMxm podcast. I'm your host, Mel the Engineer, and here on STEMxm, my goal is to showcase some of the many career paths in science, technology, engineering, and math, while highlighting women who are doing really awesome work in their respective fields. So I also try to get our guests to talk about some of the scientific or technical aspects of their work. And joining us today is Dr. Jessica Carilli. Dr. Carilli has special expertise in coral reefs, particularly how human activity impacts coral health. Okay, so we'll get into that in just a moment. I want to mention some timely things. So I'm releasing this episode in late June of 2017, and recently I was nominated by the Water Environment Federation to participate in a program called Unleash, and I found out that I was selected, so really excited. This is amazing. I get to go to Denmark and meet with a bunch of other young professionals to work on the United Nations Sustainable Development Goals. So I'm pretty stoked. I bring this up for two reasons. First, logistics. I'm going to be out of the country for most of August, so I'll probably suspend release of new episodes during and for a little while after the trip because I'll need some time to catch up. But also, I'll be posting about the trip and the program via my social media channels. If you want to follow along, be sure to follow on Instagram, where my handle is STEMxm, and then also on Facebook, where you can like and follow the STEMxm page, or also my personal page, Mel the Engineer. I'm not sure how much I'll post on Twitter, but you can find me there as the STEMxm podcast. That's at STEMxm podcast on Twitter. Okay, that's the big news for now, so let's get into our chat with coral reef expert Dr. Jessica Carilli. Welcome, Jessica Carilli, to STEMxm. Thank you so much for joining us.
Thank you for inviting me.
So I want to start with a little bit about your background. Can you talk to us about where you grew up and maybe your initial draw to sciences?
Sure. So I grew up in the Bay Area in Palo Alto, California. And in that environment, there were a lot of, this was before it was really the Silicon Valley of today. It was just sort of starting out, but there was a lot of, tech and science going on. And my mom is a biochemist, so she worked at a place developing drugs. She's a PhD. And so I kind of always was around science. My dad is an engineer at Stanford, and he works on designing laboratories and stuff. So that was, part of it was just my parents and growing up, but I also really loved to be outdoors. I felt really strongly about environmentalism, and I wanted to do something in my career that had some sort of positive impact on the environment. And I didn't really know what that was going to be. So for a time, I thought maybe I would actually go into advertising, and I wanted to do subversive environmental advertising. But then I realized that I didn't really know anything about that industry, and it was not really that appealing in the end. And I ended up taking a class in my senior year of high school, an environmental science class, and I just loved it to death. It was like the most fun thing I had ever done. So when it came time to go off to college, I decided to just pursue environmental science and try to make a difference as a scientist instead of sort of on the other side of things in terms of policy or trying to influence, personal behavior or anything like that.
Wow, that's a really interesting thing that happened to you. So this class that you took in high school really influenced your decision making there. Can you tell us, what do you remember from that experience? Was there some lesson that really stands out to you, or what was it about the class that you enjoyed so much that it made you decide to pick that as your undergraduate major?
Yeah, that's a great question. So the teacher that I had in that class, it was interesting because I had had her in a previous year. She had taught physics, and it was just not enjoyable. I didn't enjoy the class at all, and I thought she taught the class really poorly. And when I was taking her class again, and the environmental science class, I was really nervous, like, oh no, this could be quite terrible. But she was an environmental scientist. She had a PhD in environmental science. And so, of course, she taught the class with extreme enthusiasm and joy. And that just really inspired me. And every week we would go outside for one class period, and we would just go around the neighborhood and look at things outside and talk about different environmental science concepts that we had learned. Like we would just make observations as if we were a real scientist. We would have little science notebooks, and she would give us a task that we should, focus on while we were outside on our, sort of like little scavenger hunt. And it was just so fun. I just thought it was great. And I didn't know what it would actually be like to, be an actual scientist out in the field. My mom was a laboratory scientist, so that's quite different from, somebody who studies the outdoor environment. But it just really made me happy, basically. I thought, this is interesting, engaging, and I just want to do more of it.
That's really awesome. So obviously she put a lot of effort into making that a good class. How did your undergraduate work compare to that?
That's a great question. So the undergraduate program that I entered, when I first started at UCSD in my freshman year, it didn't exist at all. And I was actually going to just sort of make my own major. I decided to go to UCSD primarily because of the location, because I had just recently started surfing and I knew it was a good place to go surfing. So this was a totally non-academic reason that I chose that school. And they didn't have an environmental science major, so I had gotten permission to basically create my own. So I started doing that by just taking some really basic classes about oceanography and about climate, et cetera. And then the second year I was there, I got lucky because a brand new major appeared, and it was an environmental systems major. And within that environmental systems major, they had different tracks. And so I was able to choose the earth science and ocean atmosphere track within that. And it was pretty fantastic. One of the things that was really great about that major is that in the last year, everybody had to do an internship, and you had to write a senior thesis about your internship project. And I really enjoyed that because it was like an experience of doing actual science. Here you have to do a project and then write about what you did and explain it. We had to write a thesis, and then we also had to present our work in a poster presentation kind of context. And so that was my first taste of, what it would be like to be sort of an actual scientist. And I really enjoyed that.
Yeah, that was a really good experience for you. So talk to us about the internship. Was that something that the school set up, or did you have to find it on your own? And what did you do in that internship?
Yeah, so the internships, everybody ended up finding them on our own. A lot of people would connect up with local agencies, for example, a nonprofit, or like the city of San Diego. They work for the stormwater treatment people or something. And I ended up doing my internship on campus. I had already been working for the Natural Reserve System there at UCSD, which is like a really small office that oversees some pieces of land that the university owns and is used for educational purposes and research and sort of protection. And so I did my internship looking at, or trying to rewrite a management plan for one of the reserves. So that was really interesting to me because it really helped me realize that the policy side of things is not where I excelled. And I think I did a lot better, and I was more engaged with, laboratory work and primary research. So it was a good experience for me to kind of recognize that about myself and learn that that was what I enjoyed more.
Absolutely. I think it's, sometimes it's really important to learn what you don't like so that you can steer away from that, right?
Exactly. Yep. Yep. Yeah. And I was lucky because when I went to grad school, I went to UCSD as well. And I ended up having a couple of interns from that same environmental systems program work with me while I was a grad student. They did lab-based projects with me for their internship. So that was really fun.
Very nice. Okay, so that leads me right to my next question. Talk to us about how you decided to go for a PhD, and did you do that directly after your bachelor's degree, or was there a gap where you worked somewhere?
That's a great question. So my mom had a PhD. She was a biochemist, and she worked for a small drug company developing drugs. So as I was growing up, my real role model of a scientist was a person with a PhD. And she had told me that in biochemistry, basically it was very difficult to do much of a good job if you didn't have a PhD, and that most people would, they would go to grad school to get a PhD, and if they didn't do very well, they would end up getting a master's and leaving. So to have a master's in biochemistry, at least in her time, this may be very different now, but in her day and age, to have a master's in her field was sort of a black mark, and it meant that you didn't succeed at your PhD. So that was like the only information that I really had. And I sort of stumbled along in my quest towards becoming a scientist without really doing very much research into what that meant, what kind of jobs existed, or, what I would actually do with myself. I just had this idea that I should probably get a PhD because, my mom had one and it seemed like a good thing. And,
Yeah.
I don't know. This
It's
was
funny
a
how
really
those
terrible.
Yeah, it's funny how those things influence our decision making. Interesting. Okay, so you decide to go for it, and then what do you specialize in then when you're doing it?
Yeah. So when I was in undergrad at UCSD, during the summers, I would go home and for a few summers, I worked at a lab at Stanford where my dad worked. And in that lab, they were doing paleoclimate research. So using the chemistry of deep sea sediments to reconstruct changes in the earth over very long periods of time. And I thought that was just really amazing that you could even do that. And so got really interested in it and took a bunch of classes on paleoclimate and geochemistry as an undergrad, and decided that that's what I wanted to do as well for my PhD. Something along the lines of reconstructing change through time in some capacity. So I didn't really know exactly what I wanted to do or etc. And I met a boy while I was an undergrad, and we ended up getting married while I was in grad school. So it was good that I ended up staying around in San Diego for that reason. We're still married, but it definitely, this boy influenced my decision about, where to go to grad school and what to do with myself. So I basically sort of stumbled into going to grad school at Scripps Institution of Oceanography at UCSD because of not wanting to leave San Diego.
Well, I mean, let's be honest. That's not a crappy place to end up, is it?
No, I know. I'm extremely lucky to have gotten the opportunity to go there. It was a really wonderful experience, but not planned in any sort of academic sense, if I must be honest. You don't have to add this into the podcast, by the way. Which is just saying the honest truth. So I ended up, yep, just sort of continuing on in my career of, you know, learning about geochemistry and paleoclimate to straight after undergrad, just went straight into the PhD program, and I ended up switching topics that I was studying and labs a few times as I kind of cast about and found my path. So I ended up changing from looking at really long-term, deep time, millions of years sort of time scale questions towards the very recent past, last 150 years more or less, is what I ended up doing my PhD work on.
Okay, well,
so sorry.
Yeah, before we go forward, I want to just kind of stop here for a moment and dissect these things that you just described. So, okay, paleoclimate research. Let's start with the millions of years time scale. How do scientists do it? Like, what is the actual activity that you do to be able to look back so far in time?
That's a fabulous question. So there are a lot of different archives on the planet. These are natural archives where just the processes of the way that the Earth works have created these little historical time capsules, basically, of what stuff was like in the past. And if we can go to these archives, we can look back in time using them. So examples of these are sediments that accumulate at the bottom of the ocean. So the sediments down in the deepest part of the ocean, far, far away from the land, accumulate very, very, very slowly. So you can collect a core sample using a big, giant drilling ship that goes out there, and drill down into these layers of sediment and recover a core sample that contains, many, many meters of sediment. And because it has accumulated so slowly, just a few meters of sediment represent time from today at the very top, and layers back down in time that can go back for millions of years. So the oldest part of the seafloor has sediments on it. If you can drill down all the way to the bottom where the rock is, the sediment right above that rock is, let's say 200 million years old or so. So though the seafloor sediments, because they accumulate so slowly, we can go back quite far in time using that record, but the time resolution is very low, right? So you might be able to look at one, let's say 1 millimeter layer represents 1,000 years in time, let's say. So it's a very time averaged kind of measurement. Whereas you can also have records such as tree rings. Trees, you might know, looking at a piece of wood, they have one ring that they grow every single year. So in that case, a tree can only maybe live several thousand years for sort of the oldest trees. So you can't go that far back in time with a single tree, but you can get information at very, very high resolution at an annual time scale. So there's a lot of these kinds of archives, including ice cores, from the ice caps in Greenland and Antarctica, where layers of snow accumulate year after year and they build up and compress and form ice that has layers, annual layers, just like trees. There's also records that you can find in the bottom of lakes that have sediment layers similar to the bottom of the ocean. Or what I work on are corals. So corals are just like trees, basically. They have annual layers that they grow every year through time, and they can live for hundreds of years. So you can collect a core sample from an underwater coral and similarly go back in time using these annual layers, and we can measure the chemistry of the skeleton of the coral, and that chemistry is influenced by the water temperature and the water salinity and the amount of pollutants in the water. So, for example, heavy metals or the amount of sediment in the water, these sorts of things. We can reconstruct a lot of different environmental conditions using the chemistry of these different archives.
This is the STEMxm podcast. I'm your host, Mel the Engineer, and today we're hearing from Jessica Carilli, an expert in how environmental changes impact coral reefs. Okay, so I want to add that one of our previous guests, Dr. Marianne Holmes, she's a geoscientist. She also talked about going and getting core samples to look at some different things, but we didn't talk very much about looking at the time scale. So when you pull a core sample like this, how is it dated?
It's a good question. So for sediments, for example, you have to date them in a couple of different ways. There's, in some cases, you can date material in the sediment. So you can do, for example, carbon dating if you have something that is like a piece of wood, let's say, or a little shell or something that has carbon in it. And if it's not that old, you can use the amount of radioactive carbon, which is produced in the atmosphere, and it's included in all living things. And then it slowly decays over time after that thing dies.
Okay.
So that's how they date, mummies and things like that.
Absolutely. So I just want to ask, when you say not too old and that you can use carbon dating, how far back are you talking?
Good question. So I believe that it's about 50,000 years old is the limit of carbon dating. So if you want to age things that are older than that, then you need to use other types of radiometric clocks that have a longer, they decay more slowly. The reason that you can't date much older things using radiocarbon dating is that all of the radiocarbon will have decayed if it's older than about 50,000 years old. It's just going to be what's called radiocarbon dead. So then it doesn't tell you how old it is. You just know it's more than 50,000 years old. So,
okay. And then for a radioactive species, that has to do with its half-life, right?
Exactly.
Yeah.
Yep. The half-life tells you how fast it decays. Yep.
Okay. So before we move on to the coral reef specialty that you have, can you tell us anything about the ice core sampling that you talked about in the snowpack? How do we look at that and analyze that? How do we date that?
Great question. So with things like snow and ice, what's the word I'm looking for? The accumulation rate of snow changes seasonally. And so because of that, the snow ends up having sort of layers in it, just like layers in a tree, basically. So you'll end up with these layers of snow that differ in their textural composition, more or less. And as the snow builds up over time, it gets compressed into something called firn, and then that firn gets compressed even further into ice. And so as the snow transitions into firn and then transitions into ice, those layers, those different sort of changes in the textural composition are sort of maintained. So you can actually see layers within ice cores, and that's how they're dated. They're literally just counted. The layers are counted, and that's how we date things like sediments that are collected in what's called an anoxic environment. So that would be like at the bottom of a lake if there's no oxygen. The sediments are preserved very beautifully because nothing lives in the sediments like worms or clams or anything that would stir them up, because things can't live when there's no oxygen. So you end up just having these beautiful layers that contain seasonal differences in sort of coloration, et cetera. And so you can just visually see the layers, just like you would with a tree. You just count backwards in time. And that's how we date corals mostly when they're collected alive. We just count backwards in time from the date that they were collected when they were alive using these annual layers.
Okay, so you're saying that corals have layers that you can see when you dissect them?
Sort of. So you can collect a core sample. So the corals that I work with are large boulder-shaped things, like maybe imagine a big lump. And so you can collect a cylindrical core out of the middle of those boulders. And then we take those cores and we can either section them, so cut out a slice from the middle of those cylindrical cores, and then x-ray that slice, or we can just put the whole core into a CAT scan machine, just like you would for a person or something, and we can create, either using the x-ray or the CAT scan, an image of the density differences of the skeleton. And that's how we see the annual layers in a coral. They're not actually visible with the naked eye. You have to use an x-ray or a CAT scan to look at the just slight differences in the way that the skeleton is built, which is affected by seasonality.
Okay, so is this what you did your dissertation on?
Yep. So my dissertation work, I did two main things. One of them was to look at changes in how corals were growing through time. And the second thing was to then reconstruct the water temperature and water quality that those corals had been growing in through their lifetimes. So I was looking for a relationship between changes in the environment based on changes in what humans have been doing, so climate change and runoff from land, and then how the corals had responded to those changes using the growth rates, so the speed at which the corals were growing through time.
Okay, and talk to us about what you found. And what I want to get into is, um, for our listeners who may not know the intricacies of this, how climate change impacts the corals, because it's beyond just a temperature change in the water. So let's talk about that.
Yeah, what I found was interesting in a lot of ways. So what we kind of expected was that we would, reconstruct runoff. This was one of the main things that I was interested in, is that in the Mesoamerican reef, so this is offshore of Belize, Guatemala, and Honduras, and Mexico. I was looking at parts of the reef in Belize and Honduras. And in the watersheds surrounding the Mesoamerican reef, there's been a lot of development, a lot of deforestation and conversion for agriculture and for industry, et cetera. Particularly over the last 50 years, things have really sped up.
And
So,
just really quickly, could you explain
yeah.
how deforestation impacts runoff?
Great. Yes. So when trees are removed, this exposes the soil to rainfall. So when it rains on exposed soil, that increases the amount of sediment that runs off into the water. And coral reefs are adapted to have very clear and clean water quality conditions. So when forests on the adjacent land are removed and the runoff that is naturally occurring just from rainfall, when that runoff, instead of infiltrating down into the soil, instead it runs off over the land and it brings along that soil with it into the ocean, the corals that are living out there do not tend to like it very much. So sediment runoff can be quite a problem for corals. And the question was, on the Mesoamerican reef, was this an important stressor for the corals? Because the Mesoamerican reef is relatively far offshore. It's a barrier reef. So there's a wide lagoon between the land and the main part of the coral reef. And so a lot of people thought, oh, the sediment plumes are going to sort of just dissipate before they get out to the reef. So we don't think that runoff from land is going to be an important thing that is affecting the Mesoamerican reef. So what I wanted to do is to test that and see, did it seem like indeed land-based runoff was not something to worry about on the Mesoamerican reef? And if it isn't something to worry about, then we shouldn't be focusing conservation dollars on reducing land-based runoff. But if it was actually an important stressor and it was being overlooked, then all of the other efforts that people were making to protect the reef, such as, making marine protected areas and focusing on reducing fishing and things like that, none of those would actually necessarily help if that wasn't the problem, if that makes sense. So this is a long story to say that what I decided to do as part of my PhD project was to try to reconstruct how much land-based runoff was affecting the Mesoamerican reef in several different locations along the reef through time. So I collected core samples that were about 100, 150 years old. I had 4 different locations, and I reconstructed sediment runoff using proxies. So proxies are sort of a stand-in. We can't directly measure how much sediment was running off onto the reef, but we can measure different metals that are related to sediment, and that gives us an idea of how much was running off. So we found that there was an increase in sediment runoff at all 4 of our sites through time, and that at the sites that were closest to the major watersheds, they had higher levels of metals in them, corresponding to higher amounts of sediment runoff. So this indicated to us that, the sediment was indeed reaching the reef, and that probably the sites that were closer to these big river mouths were going to be worse off. So combined with that, that was one sort of aspect of the study, was looking at the environmental conditions there in the sediment records. And then I wanted to look at how the corals have responded to that by looking at changes in their skeletal growth rates through time. And what was really interesting is that we had expected that the corals would just sort of slowly start to grow slower and slower through time as that sediment runoff increased slowly through time. But instead, we didn't see that at all. We saw that the corals just grew the same rate through time. They did not care that the sediment was increasing. They just grew the same until 1998. And in 1998, there was the first massive worldwide bleaching event. So what happened at this time was that the water temperature got very, very hot, which was related to a strong El Niño event. And in many parts of the world, the corals that lived in those areas in which the water temperature got unexpectedly hot, they could not handle it, and their symbiosis with their symbiotic algae that live within their tissues and which give them their color, that symbiosis breaks down when it gets too hot. So the corals ended up expelling those algae. When the corals spit out their algae, they no longer have the color that comes from the algae, and their tissues are actually clear. So you can just see through their clear tissues to their white skeleton underneath. And that is why we call it coral bleaching. It looks like the corals have been bleached with, household bleach. They look all white. And the problem with coral bleaching is that the corals get most of their nutrition from those symbiotic algae. So when they've spit out the algae, then they go into a starvation mode. So if they can survive long enough without their algae, if they can live off their fat stores, or if they can switch to heterotrophic feeding. So that means they can actually capture little zooplankton from the water column and eat those directly. If they can get enough energy from that, then they can survive. And when the water temperature cools down again, they will get their algae back from the water column. It will recolonize the coral tissues and things will go along as normal. But if they stay bleached for too long, and they can starve to death, or they can become more susceptible to disease and they can die that way. So in 1998, a lot of corals died throughout the world. It was a huge bleaching event followed by a massive mortality event of a lot of corals. And what we saw in the core samples that we had taken from the Mesoamerican reef is that almost every single coral, I collected 96 approximately samples, every single coral bleached. And
wow.
the corals, it was really surprising. So they had basically not cared about their sort of degrading habitat, water quality through time up until then. And then everybody bleached. And then the really interesting thing was what happened after that. So at the sites which had better water quality comparatively because it was further away from that sediment runoff, those corals recovered and regained their normal growth rates that they had had prior to this massive bleaching event. And at the two sites that were most impacted by local impacts, so runoff, et cetera, those corals did not recover. So when a bleaching event occurs, the coral stops growing its skeleton, basically. And after that event, we saw that the corals just grew very, very small layers of skeleton for years after that at these stressful sites. So this sort of told us that, coral bleaching, which is caused by climate events, basically, and is becoming more common as the water warms because of climate change. These events can be made worse when the local conditions, like the water quality or other conditions, are poor as well.
So it basically has an exacerbating effect.
Exactly, yes. So the local conditions can have an exacerbating effect on these sort of, global scale climate phenomena.
Okay, I've got several questions for you.
Yes, sorry.
You're listening to the STEMxm podcast. This episode is the third in a series where we're touching on science related to climate change. You can listen to this episode again on iTunes, Stitcher, or directly on the episode's show notes page at STEMxm.com/episode 25. I'd be so grateful also if you'd consider sharing the STEMxm podcast as a resource to students, teachers, or school counselors who might find this information beneficial. I'm Mel the Engineer. Thanks for listening. So my first question is, do scientists expect for the El Nino effect to become greater as climate change progresses? Is it going to become, I guess, more intense?
Yeah, well, that is the $64 million question, as they say. That's definitely something that a lot of people are curious about and actively studying. And some people think that, there is a lot of compelling sort of reason to think that as the climate warms, we should expect more frequent or stronger El Nino events. I can hear my son. He's awake now. Hold on 1 second.
Okay, no problem.
Hey, Ryder. I'm in the guest room. Do you want to come down in here?
Okay, so you were saying that that scientists believe that some of these events will become more intense. So El Nino could be one of those things.
Yep. So as the planet gets warmer, we expect that storms will become more frequent and more severe, And, basically the climate will become more extreme. So weather events will become more extreme. And El Nino is not really considered a weather event. It's like more of a climate mode. But we think that there is some evidence, at least, that in times in the past when the climate has been warm on average, then El Nino events have been either more frequent or stronger. So we think that probably we should expect El Nino also to become stronger and or more frequent.
Okay, so my next question is, you mentioned zooplankton. Is that creature, that tiny little creature, impacted by any parts of climate change?
Oh, that's a good question. And that's not something that I know a lot about. My vague recollection of the literature is that, yes, it looks like as the climate is warming, the overall sort of standing stock of zooplankton in the ocean is decreasing. But I don't know if if you should quote me on that.
Well, so let's go kind of forward from there. If that is the case, if it is decreasing, what does that impact?
Well, zooplankton are basically the sort of the second rung in the food pyramid of the ocean, right? So the very base of the food pyramid would be the phytoplankton, so all the little single-celled algae, basically, that are in the ocean, the primary producers. Zooplankton then feed on that phytoplankton. So the zooplankton are just the little tiny animals that live in the ocean, like little bugs, basically. They eat the phytoplankton, and then everything else basically eats the zooplankton. So, everything from whales to fish, etc., corals, all feed on that zooplankton. So if we lose the zooplankton, then there's not enough food to support the higher trophic levels, the bigger animals, basically, in the ocean.
Okay, everyone, we've got just a tiny little pause here as Jessica had to go take care of her son at this point in the recording. So we're just going to pick right back up where we left off.
Remind me.
Yeah, okay, so we were talking about you were describing zooplankton as one of the kind of foundations of the ocean food chain.
Yep, exactly. Yeah, so exactly. If there was some, catastrophic failure of one of the lower rungs of the oceanic food web, then yes, we would see, negative impacts up the food chain, which would affect things that, humans care about more directly, like fish, etc. So that's very worrying.
Absolutely. Okay, so I want to go back to your coral a little bit. I'd like to hear your thoughts on ocean acidification. Was this a part of what you looked at when you did your research, on what could be impacting the corals, or is that any part of the type of research or work you've done since your PhD?
Thanks. That's a great question. Yeah. So ocean acidification is sort of the evil twin of global warming, caused by carbon dioxide going into the atmosphere and then getting dissolved in the ocean and lowering the pH of the ocean. And we worry about how acidification will affect things that construct their skeletons out of calcium carbonate, because calcium carbonate, which is like calcite, et cetera, dissolves in acid. So if organisms that create shells, which is a really vast number of organisms in the ocean, if they are having a more difficult time growing their shells, then they're going to, be really negatively impacted, for example, because they're going to be using more energy to construct their shells, and instead of using that energy on, reproduction, for example, or they might be more exposed to predation, et cetera. So we do worry about that, and it's something that the coral community has really been looking at a lot is, what is the impact of ocean acidification on corals? And so far, there is not a lot of consensus because it seems to be relatively, how should I say this? It seems to vary by species how the corals react to ocean acidification. But so far, it seems that most coral species can handle it. They basically don't necessarily care that much about ocean acidification in terms of building their skeletons while they're alive. So a living coral, the skeleton is protected from the ocean water by the living tissue layer. And the coral actually increases the pH of the solution from which the skeleton is precipitated anyways, compared to ocean water in the space between the tissue and the skeleton. So that's what it normally does. So if the ocean water is slightly more acidic, it doesn't actually use up that much more energy for the coral to increase the pH just a little bit more in order for the skeleton to precipitate. But the reason that we're worried about ocean acidification for coral reefs is not really because we think it will impact living corals, but we are really worried about how acidification will affect the dead reef structure. So most coral reefs, when you're thinking of like a standard, coral reef, it is built on dead corals. So basically, a living coral is on top of hundreds and thousands, maybe even millions of years of buildup of dead corals underneath of it. And if the ocean waters become more acidic, then that water will more easily erode away that structure underneath the corals. And if there's, that three-dimensional structure that the coral reef provides is the reason that coral reefs are so important as biodiversity hotspots in the ocean. They're basically the rainforests of the sea, primarily because they are providing habitat for other species. So if that three-dimensional structure of the coral reef breaks down because it's being eroded away by this acidifying ocean, then that really important feature that, what is the word that I'm trying to think of?
Like structure or foundation?
Yeah. The ecological good that they're providing is not going to be there anymore.
Right. Okay. So that's a pretty serious implication. So let's zoom out for just a second. Can you describe for us how scientists have come to understand and how they know that atmospheric CO2 ends up in the ocean? It kind of acts as a sink, but how do scientists know that, and how have they measured it over time?
That's a great question. So, okay. Hopefully I will not totally butcher this.
You can do it.
So we can estimate how much carbon dioxide is going into the atmosphere based on how much we are using, how much biomass we're burning, etc. And we can also measure the changes in the concentration of carbon that's going into the atmosphere directly using just air samples from the air. And we can also get a picture of how much dead carbon, which is what fossil fuels are. Fossil fuels are radiocarbon dead. So as we burn them, we're introducing more of this old dead carbon into the atmosphere. And we're actually changing the isotopic composition of atmospheric carbon dioxide. So the chemical signature of the atmosphere can give us an indication of how much biomass and fossil fuels we have burned and added into the atmosphere. So we have a couple of different ways of trying to estimate how much carbon dioxide we should expect in the atmosphere, and then how much is actually there. And there's a difference in that. So the difference is wherever that carbon is going, that's not ending up remaining in the atmosphere. We know it's getting burned, but it's going somewhere else. So some of that is going back into biomass. It's, going into trees, et cetera. And a lot of it is going into the ocean. And so we can look at, we can sort of check our math here on, okay, we think there should be this much in the atmosphere if it all stayed in the atmosphere, but it's not. We think probably this much is going into the ocean, and we can check that based on like a mass balance approach, but looking at the changes in the isotopic signature of carbon reservoirs in the atmosphere and in the ocean, and also looking at the pH change in the ocean, et cetera. So I hope that sort of makes sense.
Yeah, absolutely. So what else, what message would you want to get out to kind of a general listener that's interested in science and interested in understanding better how we know what we know about climate change impacting the ocean aquatic environment, and perhaps in particular to your specialty area of corals?
Oh, thanks. That's a good question. So I think what's really important to know about climate change is that, there's most people understand that the climate change is real and it's happening and it's caused by humans. A lot of the nuance behind that is complicated and confusing, and that is where the scientists sort of, this perception of scientists not agreeing with one another comes up. It's because we maybe don't agree on the little nitty-gritty details of how things are changing. So I mentioned, for example, with corals, ocean acidification and how that is going to affect corals. And that's an active area of research where some people think, oh, this could be a really big problem. And other people think, well, there are bigger, more immediate problems such as coral bleaching. That is a bigger problem right now than ocean acidification for corals. So we should focus on studying that instead of this longer term, more sort of smaller scale insidious problem that's going to come up later. So that's sort of what the scientists are doing, is sort of these relatively small sort of studies that just all build on one another. So I think that's another important thing, is sort of trying to understand this really big and complex problem of climate change. It's affecting every habitat on the planet, and there's just so many, there's millions of different species on the planet, and there's all these different, processes going on. There's the weather, and there's the rocks, and there's the living things, and everything is interacting with one another. And so the Earth is just very complicated. And so when we say that we don't, fully understand how things are going to change, and we can't perfectly predict everything, it's just because the Earth is complicated and messy. And it's not because the science is bad or we don't know what we're doing. It's just that, in order to get a perfect picture of this entire planet changing, it's just not really feasible. So the scientists we're doing our best to study sort of important aspects of climate change and important sort of sentinel species that we think are going to be the most impacted, and trying to sort of see what we think is going to happen and whether there's anything we can do about it aside from, removing all this extra carbon from the atmosphere, which is something that a lot of scientists are working on and I think is very important. But there's, a lot of work right now is just looking at sort of trying to predict what's going to happen so that we can be prepared, because it will really allow us to sort of adapt our expectations and make changes in the way that we operate with our lives if we know what's coming. So I don't know, this is kind of very random rant going off on a tangent.
No, that was great. Thank you for explaining that and sharing that with us. So that comes about to the end of my question. So I wanted to ask, I noticed that you have been involved with a couple of blogs. You have your own that I think you still write on, the jessicacarilli.blogspot.com. And then are you still involved with the saltwater science blog as well?
Yeah, so unfortunately, the saltwater science blog was hosted by Citable, which was one of the nature websites, and they decided not to continue supporting that website. So basically, all the existing blogs are still there, but we aren't able to post any more up there. So that's too bad. So the saltwater science, the posts are there, and I would encourage people to look at them, but we won't be able to post any further ones. And my personal blog, I have been neglecting it for ages because I've just been too busy at work. But I do hope to get back into it one day when my little ones are maybe a little bit less interested in hanging out with me, because I really do enjoy writing on it. But
yeah,
it seems that I spend every moment with them or working, so it's hard.
Yeah. Okay. Well, I'll put links to both of those in the show notes. And then would you mind telling us your Twitter handle so that a listener could reach out to you if they have a question?
Sure. It's at Jess_Carilli.
Okay. And that Carilli is spelled Carilli.
It is. Yeah, exactly.
Excellent. Okay. Well, I want to thank you again, Jessica, for joining us on the STEMxm podcast. I really appreciate it. Thanks for teaching us about the science of corals.
Thank you so much for having me. It's something that I love to talk about.
I hope you enjoyed that chat with Dr. Carilli. As we mentioned here at the end, I put links to Jess's Twitter account and the blogs that she's written for on the show notes page. You can find this episode's show notes at STEMxm.com/episode 25. That's STEMxm.com/episode and then the number 25. So remember, I'll be updating everybody with details about my trip to Denmark to work on the Unleash program for the UN Sustainable Development Goals on my social media. So head on over to STEMxm.com where you can find the links to all of my channels there. And again, I want to thank you for downloading and listening to this episode of STEMxm. If there's a particular career that you would like to hear about, I'd love to hear from you. You can reach out to me on Twitter. The handle is STEMxm Podcast. And you can also go to the website where you can find out details about all the episodes, and you can contact me there via email. And then you can also sign up for the STEMxm newsletter. So thank you again, listeners, and I'll be back with you in episode 26.
This has been an episode of the STEMxm podcast. Thank you for listening. We would really love if you could pop over to iTunes and give us an honest, positive rating. It helps more listeners find us to learn about STEM careers. Thanks again, cheers, and we'll catch you on the next episode.
Can you speak at all to how Henry's Law plays into this?
Oh, no.